The atom. Do you recognize this molecule? It is a water molecule. When making molecular models, spheres are used to represent atoms and rods are used to represent bonds. But today we are going to zoom in a little closer to see how atoms actually look. In this image, each blue sphere with H represents hydrogen, which is an element on the periodic table. The red sphere with O represents oxygen, which is also an element. There is one oxygen atom and two hydrogen atoms in a single molecule of water. Notice how the oxygen atom is bigger than the hydrogen atoms. Different elements combine together to make up all the materials and objects in this world. But keep in mind that atoms are extremely tiny. It is impossible to count the number of atoms that exist in the period at the end of this sentence. John Dalton was an English chemist, physicist, and meteorologist born in the 1700s. He formed a theory of atoms that explains four key concepts. Dalton's atomic theory. 1. Atoms are tiny particles that make up matter. 2. The atoms of one type of element are all the same, but the atoms of one element type are different than the atoms of another element type. 3. Atoms do not change into other atoms during chemical reactions. Example, oxygen will not turn into hydrogen. 4. In chemical reactions, atoms can form bonds in other atoms to form compounds. Atoms bond together to form molecules, but when atoms of different element types bond, these specific types of molecules are also called compounds. For example, water, H2O, can be called a compound as well as a molecule, but oxygen, O2, being composed of only one element type, can only be called a molecule, not a compound. Chemists use different ways of representing molecules, like the ball and stick model and the space-filling model shown here. In order to highlight different aspects of the molecular structure, even though this image does not use rods, it still represents oxygen and hydrogen molecules that are bonded. Have you ever felt static electricity? It is the result of an electric charge. Electric charges are either positive or negative. Opposite charges attract each other, while similar charges repel. A similar force can be felt on a magnet. In the 1800s, experiments were done that led to the idea that atoms have electrical charges, but scientists were still figuring out how these charges were arranged inside an atom. A scientist named J.J. Thomson thought the atom was made up of negatively charged particles that were scattered about in a sea of an equal number of positively charged particles. These negative charges could be visualized as seeds in a watermelon, where the red part of a watermelon is the sea of positive charges. However, there were some faults in this model, and Ernest Rutherford proved a more complete structure of the atom. Rutherford shot a beam of positively charged alpha particles through a thin sheet of gold. He noticed that most of these particles passed straight through the sheet. Think of a flashlight shining through a window. However, some of the positively charged particles bounced off the gold sheet at wide angles. Remember, similar charges repel. So Rutherford postulated that the positively charged particles must have struck something in the gold sheet that was also positive. Since most of the particles passed through the gold, Rutherford concluded that most of an atom was empty space, and the positive charges had to be very small and located in the center of the atom, which is now called the nucleus. Beam of alpha particles, gold foil, screen. Some alpha particles are deflected. Most alpha particles hit here. The alpha positive beams are repelled by a positively charged center of an atom, the nucleus. nucleus, surrounding electrons. Rutherford's experiments gave way to the idea that the atom must have a centralized nucleus with a positive charge and negative charges surrounding this nucleus. The word nucleus means the central part of an object. The nucleus of an atom contains positively charged particles called protons and particles with no charge called neutrons. Surrounding the nucleus in an area called the electron cloud are negatively charged particles called electrons. See if you can identify the nucleus, protons, neutrons, electrons, and the electron cloud on the picture above. Electron, neutron, proton. Most of the particles in Rutherford's experiment went through the gold sheet. This tells us that most of the particles went through the electron clouds rather than deflecting off the nuclei. Therefore, most of the space of an atom is taken up by the electron cloud. The nucleus takes up a very small amount of the atom, but it is much more dense. Electrons are constantly moving in sections around the nucleus called orbitals. Orbitals are areas where electrons are most likely to be found. An orbit is a predictable path, whereas an orbital is an area where the electron could be found. Since electrons are in constant random motion, their exact location is unpredictable. Important facts about electrons and protons. An electron is smaller and lighter in weight than a proton. Electrons and protons are equal in electric magnitude. Being opposite and equal, they cancel each other out. This means an atom has no overall electric charge. Electrons are attracted to the positively charged protons in the nucleus. Because positive and negative charges attract, electrons closer to the nucleus are held more strongly than the ones farther away. Neutron, proton, nucleus, electron. An element's atomic number is unique to that element. Carbon has the atomic number of 6. No other element has the atomic number of 6. The atomic number defines the number of protons an element has. Because an atom has no overall charge, there must be an equal number of electrons. Therefore, carbon must have 6 electrons, 6 protons, 6 neutrons, 6 electrons. Atomic number is 6. C symbol, element name, carbon, atomic mass, 12.01. The atomic mass is the measure of how heavy an atom is. Because an atom is so tiny, a special unit of weight called the atomic mass unit, AMU, is used to measure its mass. Carbon's atomic mass is 12.01 AMU. Only protons and neutrons contribute to atomic mass. Electrons are too small and light to add any significant weight. While an atom has the same number of electrons and protons, the number of neutrons can be different. However, this difference in the number of neutrons does not change the identity of the atom, because it is defined by its number of protons. Individual forms of an element having the same number of protons but a different number of neutrons are called isotopes. Carbon is an element that can have a different number of neutrons. Carbon that has 6 protons and 6 neutrons is called carbon-12, while carbon that has 6 protons and 8 neutrons is called carbon-14. Because neutrons contribute to weight, isotopes with more neutrons are heavier. The atomic mass printed on an element symbol on the periodic table is a weighted average of the atomic mass of an element with all of its known isotopes. Carbon-12, 666, stable. Carbon-13 is 676, stable, and that's what it looks like. Carbon-14, 686, and it's radioactive. Electrons do not orbit the nucleus. Instead, they zip around the nucleus in areas called orbitals. Orbitals are grouped into sections in the electron cloud called electron shells. The first electron shell is closest to the nucleus, and each subsequent shell moves outward from the central nucleus. To visualize electron shells, think of a set of Russian stacking dolls. Electrons generally fill orbitals starting with the first shell, then filling outward to the second shell, then the third shell, and so on. Electron structure does have more than 3 shells and can become very complex, but we will just focus on the first 3 shells. As electrons fill additional electron shells, we say electrons are in higher energy levels. Try to memorize the information in the table below. Electron shell, electron capacity. First electron shell, 2 electrons total. Second electron shell, 8 electrons total. The third electron shell, up to 18 electrons. Note, we will focus on the first 8 electrons. Additional information regarding electron shell capacity and orbitals can be found at the end of the lesson if you would like to learn more. As you study and learn more about atoms, you will find that science is full of patterns and many amazing hidden discoveries are yet to be made. It is incredibly fascinating to ponder how studying science leads to the discovery of these hidden secrets God has used in creation. It is amazing to think that God created and arranged all the particles in such a way that we and all the things around us can exist. As you learn about atoms, you gain proof that God works in wisdom and order. Coming to understand the basics of chemistry lets you better understand and appreciate how He has masterfully created the beauty we enjoy. You are blessed as you acknowledge Him, in whom are hid all the treasures of wisdom and knowledge. Colossians 2:2-3.